Welcome to my YouTube channel Mechanical Magic Mechanical Learning Tutorials. So in this video I am talking about Carnot vapor cycle. So basically in case of Carnot vapor cycle, so working substance that will be steam or any other vapor form is being used as a substance. So as we discussed into the previous video, Carnot cycles. So basically in the case of Carnot cycles, two isothermal processes and two adiabatic processes is being occurred. So as from the figure, or you can say the process for Carnot cycle like this. So here it will be the one kind of boiler is being used. So here boiler is being used. So you can see that heat being supplied to the boiler, and that will be having an application to developing a high pressure, high temperature steam. So that will be at constant temperature, or you can say isothermal process. So after that high pressurized, high temperature steam, it will be passing through the turbine. So that will be converting into some mechanical work by expanding of that particular high pressurized, high temperature steam. So with the application of turbine, it should be rotated and some kind of work output. So that will be our 2 to 3 process. So after that, expanding once again, that remaining steam, it will be into condenser. So once again it will be converting into the water by rejecting a heat. So heat should be rejected. And you can also write down steam to water. So in the case of condenser process, so that will be 3 to 4. Once again, from that water, it should be supplied into a compressor. So that will be some work it being input into the compressor. So with the application of compressor, that will be increasing the pressure from P2 to P1. So that will be the completing of the cycle. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1 process. So let us see. It will be on to a PV diagram. So here x-axis and y-axis. So here it will be volume V, pressure P. So 1 to 2 process, that will be the isothermal process, or you can say constant pressure process. So 1 to 2, that will be coming into the picture like boiler, or you can say thermal expansion process, and then after 2 to 3 process, that will be called as a turbine, or you can say adiabatic expansion process, or simple way isentropic expansion process. So 2 to 3, and after that will be condenser. So 3 to 4. So generally that will be isothermal, so it will be converting at T1 temperature, and here it will be the T2 temperature. So once again, isothermal compression process, and once again 4 to 1, that will be adiabatic compression process. So that will be into compressor, right? So here P1 that should be equal to P2, and here P3 that will be equal to P4. So now, as from a figure, that will be a flow diagram, or you can say diagram, and here PV diagram. So for process 1 to 2, or you can say boiler process 1 to 2, and from PV diagram 1 to 2, constant pressure heat addition process in the boiler. So also constant pressure process and constant temperature process. So the water that should be converted into a steam, or you can say high pressurized, high temperature steam. So after boiler, that will be into turbine. So by the application of that heat addition, turbine has to work. So during 2 to 3 process, or you can say into turbine, that will be adiabatic expansion process. So in case of adiabatic expansion of steam into turbine, so turbine gives some of the work output. So you can say that turbine work. Then after at point 3 to 4, and that should be our condensation process at constant temperature and constant pressure. So in that case, at constant temperature and pressure, that heat rejection into condenser. So now it will be having a T2 temperature, so lower temperatures. So at lower temperatures, that heat is being rejected, and that particular steam once again converting into the water. So at 4 number point, or you can say end of an isothermal compression process, then the adiabatic compression take place. So once again, that P3 temperature, it will be increasing up to a initial temperature, or you can say at P1 temperature. So steam and water enter into the compression, so that should be increasing the pressure, and for that compressor consumes some of the work power. So that will be work on compressor as a input. So that will be the simple Carnot vapor cycle over here. Now after the simple Carnot vapor cycle, efficiency of Carnot vapor cycle, so here some of the consideration like that 1 kg of working substance. So over here generally work done by turbine, or you can say WT, that will be equal to H2 minus H3, and work input to compressor. So that will be work done onto the compressor, so that will be equal to H1 minus H4. So as from the PV diagram, it will be the clear that work done by the turbine, it will be H2 minus H3, and work done as a input to the compressor, so it consumes the work, or you can say power, so that will be H1 minus H4. So net work developed that will be equal to W net, so turbine work minus compressor work. So here H2 minus H3 minus H1 minus H4. So now the condition for heat supplied, so heat supply that will be equal to H2 minus H1. So now I am interested for the efficiency of a Carnot vapor cycle. So over here there is a symbol of an efficiency, so equal to net work developed divided by heat supply. So over here net work developed, so that will be from equation number 1, H2 minus H3 minus H1 H4 divided by H2 minus H1. So from here H2 minus H1, rearrange of these equations, H3 minus H4, and divided by H2 minus H1. So finally you get 1 minus H3 upon H minus H4 divided by H2 minus H1. So this you can referring a cycle. So from here QR that will be equal to H3 minus H4, and heat supply that will be equal to H2 minus H1. So just put the value into this equation and finally efficiency you will get 1 minus QR divided by QS. So that will be a efficiency of an Carnot vapor cycle. But entropy is defined as ds, that should be equal to integration of d reverse divided by t, or you can say dq upon t. So from here q rejected, that should be equal to, so generally rejection at T2 temperature and in between S3 minus S4 and Q supply. So supply heat at higher temperature, you can see T1 temperature as from the diagram S2 minus S1. So just put the value of this equation into efficiency. So finally you will get 1 minus T2 into S3 S4 divided by T1 S2 minus S1. But here that will be converting into HS diagram. So just we will see that in case of HS diagram of this previous diagram, now I want to draw HS diagram. So here H S so 1 2 3 4. So S1 equal to S4 and S2 equal to S3. So that will be isothermal expansion, that will be isentropic expansion, isothermal compression and adiabatic compression. So just my interest is what? S1 equal to S form over here. So S1 equal to S4 and S2 equal to S3. So just changing, and it should be modified like this: 1 minus T2, so S3, that will be equal to S2, so S2 minus S1 divided by T1, S2 minus S1. So that should be cancelled out, and finally you will get the efficiency of a Carnot vapor cycle: 1 minus T2 upon T1. So that will be in the simplest form of an efficiency of Carnot vapor cycle. So some of the limitations of this cycle also, and that will be under in process 4-to-1 process of compression of wet vapor, which is very difficult. So in that case, that will be the condensation process, and that it will be having water plus some of the steam. So by practically that will be having a difficulties. So the practically compression and expansion are having irreversibility. not possibly practically. So to achieve the superheating of steam at constant temperature and pressure has to be reduced. And it means what? The expansion and addition is to be done simultaneously. But that will be, once again, practically it will be having so much difficulties. So these all are regarding to the Carnot cycles, efficiency of the Carnot cycles, PV diagram, line diagram and HS diagram. And the equation is 1 minus T2 upon T1. So if you like this, then subscribe and share Mechanical Magic, Mechanical Learning tutorials. Thank you very much.